Greetings and welcome. So, in recent videos, sort of been down in the weeds with a lot of stuff that people might sort of think is irrelevant, or I'm sort of spinning my wheels to make a joke. But things are all kind of coming together, and I'll show you one thing that I've seen that has me very optimistic. But before we get there, I'll just share with people some theory, and maybe others haven't said it this plainly before, and there's still a little bit to confirm, but let's just go through this. So what's the unit of magnetic field strength? Well, for the B field, it's the Tesla, or if you divide the Tesla by 10,000, it's the Gauss. For the H field, it's the ampere turn. And how do the B and H field relate to one another? B divided by U0 equals H. So they're talking about the core material there, and U0 is the permeativity of free space, so that's an air core. So when you have an air core, B equals H. And if you don't have an air core, then B will be related to whatever core material you have and will differ from H. Since we've been using air cores, B equals H. Hence, the magnetic field strength is defined by the ampere turn. Let's find the ampere turn. Well, to express it more formally, the H field is ampere turns per meter. So what's an amp turn? So the ampere turn, in addition to determining the H field strength, is the unit of magnetomotive force. And first, let's just talk about what it is. It's how many amps are flowing through how many turns in a coil. So a current of 2 amps flowing through a coil of 10 turns produces a magnetomotive force of 20 amp turns. Okay, and so if we go to, here's someone asking, explain amp turns. And they do the same thing. The magnetomotive force is equal to turns times amps. And current of 10 turns, 10 amps. Magnetomotive force of 100 amp turns. And if we go back here, we can see, where is it? Oh, come on. Well, in this discussion on magnetomotive force, we see here is, again, magnetomotive force is amp turns. It's turns times amps, but it's also magnetic flux times reluctance. And I would just bring that up there with magnetic flux. I don't want to get too much in the weeds here, but if we then talk about an inductance. So inductance is all right, sorry. So inductance is the ratio of induced voltage to the rate of the change of current, and here we see that electromotive force, not magnetomotive force, is defined as the change per unit time of magnetic flux. So we see how magnetic flux and inductance are related, and it's all very confusing. And part of that is because there are parts of it that are complicated, and part of it is that they don't really have a fundamental theoretical understanding of what's going on. So, for instance, the formulas for induction go back to a gentleman called Wheeler doing this work in, I want to say, the 1930s at what became the National Bureau of Standards, and it's all empirical. So, you talk about amp turns, but, what if you have a square? What if you have a triangle? And that, you would still call it turns, but it's your inductance, hence your magnetic flux, and hence your magnetomotive force is then all different, and it's all derived empirically. So as I said, I don't think they really, even now, or at least publicly, they don't have a fundamental theoretical understanding of what something is going to do in terms of, to be blunt, magnetic field strength. However, you got a pretty good idea after all these years of what's going on. So to cut to the point, if anyone's happened to stick around this long, there's something really curious that you can consider in terms of amp turns and coils and a pulse motor or any electric motor. And that's the following. Let's do this thought experiment and then we'll demonstrate it. Let's say you have one coil and you have, let's put an amp through it, and it has 100 turns. What's the magnetomotive force is 1 times 100 ampere turns. Now let's put a second coil that's identical to that coil in series over here. Now what do you have? You have double the resistance, correct? So you have 1/2 amp flowing through both coils. The first coil has 100 turns, the second coil has 100 turns, for a total of 200 turns with 1/2 amp. So 0.5 times 200 equals 100. So in both cases you have 100 amp turns of magnetomotive force. Or you could look at it in terms of inductance. What is the inductance of one coil? Let's say it's 1 millihenry. Put a second identical coil in series. Now it's 2 millihenries, but you have half of the amp flow. So let's say that you have one coil sitting next to a permanent magnet, and you put 1 amp through it. There'll be 100 amp turns that will be creating a magnetic field in opposition or in attraction to the permanent magnetic field that can be used to cause rotation. Now what if you put 2 coils like that? Then you have 1/2 amp and you have 50 ampere turns here, 50 ampere turns there, for a total of 100 ampere turns, in which case the coil should spin at the same speed with half the amp draw. Now, this is a very small channel, but a lot of bright people here, so I don't think I need to elaborate further on what that implies. But let's see what we can do, because one of the things, and this is why I'm so glad that I looked at the air gap, is that I wasn't seeing that. And so I'm thinking, well, there must be, obviously I'm missing something. That can't be. You think about it after all this, that, and, going through formulas and all that. It's like, no, that can't be. But we'll see. And so let me demonstrate some stuff for you. So we have this this rotor. I need to improve the rotor, but that's another story. And we'll use this coil to spin the rotor. And we have a very narrow air gap. I mean, it could be narrower, but relatively speaking, a narrow air gap. And this is not something I'm going to repeat because it was done in the last video. There's something curious with this one coil, that when it's further away, the rotor spins faster, and you bring it in and the amp draw goes down and the rotor slows down. So that's very curious, isn't it? You would think if the rotor is slowing down, the amp draw would be going up, and you would think that the rotor would be spinning faster. And what was also seen was that when a coil with this form, this darn thing broke apart, I think I was saying the 3D printer is giving me fits right now. So what I need to do is get it running consistently and print new coil forms and reprint this rotor. When this coil form was used, now it's a smaller coil, so it's less powerful, and both less powerful and less efficient. But when it was out here, it would be spinning slower, and when you brought the smaller coil in, it would be spinning faster, and again the amp draw would go down. So it behaved opposite this large coil. So then the question becomes, why is that? And you can think of, I'd say, 3 reasonable explanations, but there's one that I'm going with. The first is that this large coil, as it's coming in closer, is only hitting on one part of the rotor, and so it's giving a force that way, causing the rotor to want to do this, creating friction that is slowing it down. Now the problem with that is that the finding was so dramatic that it slows down considerably. And with the second coil, albeit a less powerful coil, bringing it in, it sped up. So there's certainly going to be a little bit of that wobbling going on, but I don't think that accounts primarily for why the rotor is slowing down. The second thing is that this coil is somehow stepping on its own toes. So you would think, is it seeing the next incoming magnet? I don't think so, because there's only 4 magnets and they're 90 degrees apart. So let's say it's pulsing, about there. This one is going to be like there. So I don't think it's seeing the next magnet. And when we go to a 6-magnet rotor, we'll have a better handle on that. So then what are you left with? You're left with, well, I showed you that the magnets are about 1 inch wide. So maybe a little bit, like my 2 fingers, are a little bit narrower. So this stuff here on the outside, the magnetic field that's coming down, is seeing the proper field, but it's also extending down to the other side of the magnet and seeing the wrong side of the field. So now it's seeing both the north and the south field simultaneously. Now, if that's the issue, then how could you solve it? And there's a few ways. First is go to a different coil form, and that's what I'm going to do, because I think that will give you your cleanest answer. And the second would be make the permanent magnet, instead of a 1/2 inch, put a second one in. And you'll also double the strength of the magnetic field from the permanent magnet. Isn't that goofy to think about? So now you've moved the permanent magnet field a 1/2 inch away, and you could do that, more of that. The third that would be more involved would be to use what's called a Hallback array, and that's an orientation of magnets such that all the magnetic field goes to one side. So you'll have like a double strong north and essentially no south, or a double strong south and essentially no north. And it's interesting to consider that arrangements of magnets, isn't it? As an aside, I was watching Monroe Live. This guy that is a company that just tears down, cars and electric cars. And he said that Tesla, with their electric motor, uses Hallback arrays. So if you used a Hallback array, then you wouldn't have to worry about it, assuming that's the problem, and we'll kind of show that it is the problem in a moment. So those are ways to get around it, but let's first just confirm that it's there. Okay, so we're spinning this rotor, and again, the rotor's not the best, but whatever. 938 seems to be, it's about where it wants to be. We're drawing, what is it? 25, 30, 35, 30, about 30, maybe 31 milliamps. The inductive is being shunted into that cap with I think 100k ohm resistor across there, and we see 24.4 volts. The reason I have the resistor in place is that sometimes when you change things, the peak voltage, say at 75, doesn't change, but if you put the resistor in, you notice there's a big change in how much power that it puts out. So again, the problem I have is that I need to get the 3D printer working correctly to print more of these coil forms, or make this magnet longer or something like that. I'm not even going to jot these numbers down, they'll be there in the video, but let's put another coil then in series with this one, put it exactly 180 degrees opposite, and from the preceding discussion, it should spin at the same speed and the amp draw be halved, but that's not what happens. So let's do that. Real quick before we do that, if I just lift this thing up, and we're going to keep an eye on that, you can see that changes. And the rotor is actually speeding up, but our amp draw is going way up. So there are a number of things bad with this. One is that the spike is going kaput as this is coming down, whereas with this coil form, the spike kept improving as the coil got closer and closer to the magnets. So that's why this is also a big problem. Not just the rotor slowing down, the spike going away. But you don't want to run it up here because the amp draw goes to hell. And while it speeds up, the torque goes to heck as well. And so you're both using twice as much power and it has half the torque. So now we put a second coil in series, and the one good thing is that the amp draw is just about half. I think I said 35 or something like that, and it's, you know, like it's 25, like 20 there, so maybe just about half. The spike has gone way down, so that's terrible. And the rotor is now slower when it should be the same speed. So the only thing that happened is the spike got worse, the amp draw went down, and the rotor slowed down. So that's no good. Now another way that you could try to minimize this, and again this is just because I don't have the 3D printer working to use the proper coil forms, is increase the air gap with these and then see what it does. And as an aside here, this also says that the main reason the rotor is slowing down is not because it's just being hit at one point, because now it's being hit at 2 points exactly 180 degrees apart, and so that would get rid of the wobble, but it's still slowed down a lot. So this is stepping on its toes, and I don't think with the magnets 90 degrees apart it's stepping on the next magnet. So it's seeing around to the other side of the coil. So if we bring this up, it won't entirely get rid of the problem, but it should greatly mitigate it. And we can see how it behaves. And again, it'd be fun to get that printed. So let's do that now. And just one last thing before doing that, is that these two coils are arranged correctly. So in other words, it's not that one is north down and one is south down, because if I flip that over, the rotor basically comes to a dead stop. I've unplugged it now, but so that is arranged correctly. So now I just used a little masking tape to make a big air gap, and that should get rid of most of this field interacting with the wrong side of the magnet. And it's just spinning up now. It has much less torque, so it takes a long time to spin up, but you can see the spike across the 100K ohm is much higher, like twice as high. And as I said, with the proper coil form, the spike across a resistor increases. Now again, this coil is smaller and so it's not as good, but it moves in the right direction. Now the amp draw is very high. The amp draw was, what did we say, 35, and now it's like 125. It's still spinning up, so it'll probably end up at like 120, 115. And I think we will see this spinning faster once it's finally fully spun up. Okay, I misspoke. With this big an air gap, it is actually slowing down. I mean, it's taken forever, but it's 543. It's still climbing. It's going to do a little more of that. Well, no, maybe that's about where it is. So maybe it gets to like 545. But if you like have this air gap, the thing would probably be, you know, you could get it out to like 1100, and then it goes down to like 900 with the real small air gap. So that trend is true. The air gap is just so big now that it's slowing down. But that's not the crucial part. The crucial part is what happens now when you put a second coil on. And just to look here, we're drawing 130 milliamps, 54.8 across the 100K ohm. So let's put in the second coil. Okay, so we put in the second coil, and now it's behaving more like that little theoretical discussion we had to start. It's headed towards 75. We're at 130, so it's not quite halved, but it's close to the amp draw being halved. Why it's not halved when you double the resistance, I don't know. But it, you know, moving in the right direction. And it should be spinning at the same speed. Oh, wait, it's not. Now it's going faster than with the one coil, and the amp draw is nearly half. Now, why is it going faster? This is where I think it gets into play that there's no longer an imbalance of the rotor. And since the stepping on the toes part has been minimized, now correcting that imbalance of the rotor, you see it spinning faster with two coils when, technically the magnetomotive force is identical. I mean, I haven't measured the inductance and resistance on those coils, but they're about the same. I think they're nearly the same. So it should be spinning the same speed, but it's spinning a good bit, 5-10% faster. 5% probably. Maybe 10%. I think it was like 530. Now, the spike has decreased a little bit across the 100K ohm. I'm hoping that that's just some residual interaction with the wrong side of the magnet, and that will go away with the proper sized coils. It could also be if the inductances aren't exactly the same, that is just going with the least inductance coil. Maybe I'll measure them. I'm not sure. I think I'll just get these going and go with that. But the drop there is nowhere near as significant as the near halving of your amp input. So now things are behaving how they should. The problem is we got a giant air gap. So it's going to be very interesting moving forward to see when we have the coils properly sized and you bring them in close to the magnets, you'll still get the amp draw. The rotor will speed up with one coil, and make sure that with the second coil it behaves like these two coils do with the giant air gap. And if it does, how do you put it? I mean, not to be dramatic, but you're good to go at that point. I mean, at that point, there's plenty of other stuff to solve. There's, we're gonna experiment the living shit out of this thing. There's gonna be 6 magnets. We're gonna do bipolar and all that. But once you have that nailed down, then that's it. From there, it's just a matter of how you care to go with it. So that's why I'm saying that's going to be really interesting once the new coils are wound. I'll show you one last thing, and then we'll wrap this up. It's going to be a 5-minute video, but no. So what are hopefully it's like steadied out now. Yeah, 582. So a good bit faster, and I think that's because the rotor's balanced. Now, I mean the thing's wobbling to heck, but the force is balanced on the rotor. Here's something weird. So, if you turn this thing, if I can do it without... Now, if you turn this thing over, they're both acting against each other. It'll come to a darn near stop. But, what if you put it here? Now, you can see those little ridges there, so I've actually moved this coil a little bit further away. Amp draw is the same. It's heading back towards 75. This, I think, is the same. Which is kind of interesting because the two coils are one's going this way, the other's going that way. Let's see what we got here. We're going to have to give it time because these things are slow. So just, to be clear again, I've flipped this coil over so that now one is in, I don't know whether this one is in push or a pull, but one's in repulsion and one's in attraction. And it actually, I can't remember what we were at before, but what I was seeing is that it's actually a little faster that way. There's no change in the amp draw and there's no change in the spike. So that's kind of curious. And when you get these 1-inch coils, so I mean you can go 1, 2, 3, 4 with the I think they're 1 or 1.5, the smaller coils. You might even be able to fit like 8 coils, one this way, one that way, one this way. Still have it as a monopole. Although of course then, it's like, well, there's all kinds of stuff you could do with that now that it's there. And I think the main point there, and it's still speeding up. The main point there is that it allows you to fit more wire in a productive fashion around the rotor than you could otherwise. Okay, I think that's it. So that's really where we're going to next. Is going to be, one coil, two coil, four coils, and we might even go to 8 volts, and that gets interesting too. Comparing 4 volts to 8 volts. So again, I hope people enjoyed this, and it might take me a while to get these things printed, so it might be a little while before I do another video. But this has actually gotten very interesting now for me. And thanks for coming along. Stay healthy. Bye-bye.